Hi everyone, and welcome to today's webinar. This will be looking at how AI is challenging capacity in data center networks and how optics line up against other solutions to the problem. As well as the obvious need for extra capacity, the AI explosion also creates challenges in data center networks, such as increased energy consumption due to high performance computing, which can lead to higher operational costs and environmental concerns. There's also the need for advanced cooling systems to handle heat generated by AI-driven workloads. Can optics help to solve this growing problem? I'm joined by two experts today to help find out. My name's Keely, and I'll be your moderator. And I'm very delighted to introduce Chun Hee, Chief Scientist at Focuslight Technologies, and Terry Thorne, Vice President of Commercial Operations at Air Labs. Thank you so much for joining me today, chaps. So we're following a bit of a fireside chat discussion with this webinar. So I'll be posing some questions to our panel to generate some discussion around this important topic. If you have any questions that you'd like to ask our speakers, please do feel free to submit them. If they don't get answered today, we can pass them on at a later date after the webcast. So without further ado, I'm going to ask my first question to both of our panelists. So what do you guys see as having the biggest impact on data center infrastructure and capacity today? Should we start with Terry and then move on to Chun?
Thanks, Keely. So I think at a global level, what we see is the growth of AI and the ability to secure the energy required to run data centers are two of the critical areas having the biggest impact on the infrastructure and the capability. And to the AI side of things, that the growing complexity of the parameter size of AI models is requiring those AI workloads to be split across tens to thousands of compute chips, which is really outstripping the ability of traditional electrical interconnects to connect and help drive those chips. So that's where the application of optical interconnects comes to play, and that's why Air Labs is putting forth as a solution.
Fantastic. And Chun, your take on this, please.
Well, obviously, I believe the AI and machine learning workload is increasing dramatically, and so we have a lot of demand for the data center to transport the data at very high bandwidth at a very fast speed. And AI model, like a large language model, they do need a lot of intensive calculations. This is one side. There's a lot of demand for calculations and for data transfer from one place to the other very fast. The other thing is the edge computing and decentralized architecture for the data center right now, because they want to decentralize the data center. So a lot of data center is very close to the user, and a lot of computations are done over there, and the data needs to be transferred to the very center of this data center. In that case, we need a very fast speed and high bandwidth transformation of the data. And also, as you mentioned, the energy consumption is an issue, because there's a lot of these GPUs, they cluster together with CPUs. They have to communicate each other very fast, and that may make these GPUs are working very hard, and they generate a lot of heat. Also, they consume a lot of electric power, and this chip need to be cooled down to make sure they are still reliable working. In that case, a lot of energy is being used, a lot of electricity energy being used. Another thing I see is the space efficiency is needed, because a lot of components, fiber optics components and fiber cables as well, they were made not for this current situation. So they are relatively, they are bulky, and they are not bulky. They have been pretty small, but not small enough. And we need to make the component smaller, more efficient, consume less. That means they need to have a lower loss, and they need to be very small. They need to be combined, integrated together to work together to make the data transfer faster and also efficient, also save electricity and save space. So I think this is the challenge for the data center right now.
Yeah, absolutely. And looking at the kind of optical solutions, the adoption of high-speed optical solutions, why is that becoming crucial for data centers in line with this? Chun, if you want to take that to start, and then we'll move to Terry, is that okay?
Yeah, I can present something right now is appropriate because we just we are working on the micro optic arena. We make a new array micro lenses and micro prisms. This new generation of micro lenses can help us to build a component, as I mentioned, more efficient, can be very space saving, electrical saving, because they have a lower insertion loss. So that will help open another arena for this increasing the bandwidth for the network. So we call, I call it the spatial division multiplexing. I think this is an avenue we haven't fully explored before. Up to now, we have been using like advanced modulation technologies. We have been using WDMs, but we haven't explored this spatial division multiplexing technology fully. And we are, our companies realize this. We try to develop newer micro optics array and to do integrate the components, and we want to achieve that goal. And we can demonstrate that is really possible. And in fact, I bring some new slides that never shown before, and to show these devices. You think it's I can show them now?
If you, I'll tell you what, we're really excited to hear what both of you guys are doing to help the data center networks. And that was going to be my next question. So you beat me to it there, Chum. But let me just get Terry's feedback on the question, and then I'll come back to both of you about the work you're doing with data centers, because I know the audience is really excited to hear about it. So Terry, what's your view in terms of, high-speed optical solutions and why they're so important?
Well, I think there's a what we see at our labs is that traditional data centers today on the scale-out networks, they're using silicon photonics and they're using optics. But on the scale-up network, where you're looking at how do you connect multiple GPUs together to really work as one GPU, that's still a copper electrical-based interconnect. And so the increase in parameter size of AI models and the complexity of those models is kind of unrelenting. So in order to address those models, you've really got to split the workload across tens or hundreds or even thousands of compute chips, which outstrips the ability of copper and electrical interconnects to do that. So where we see that, where we see our technology playing out is in that scale-up network where you are combining those compute chips together and scaling those across, scaling the workload across multiple, tens or hundreds of thousands of compute chips. And so that's really exciting for us in the space of optical interconnects inside the scale-up network or memory semantic network. And really the technology we have today, if you want to deliver the promise of AI in the future that everybody's anticipating and looking forward to, you really cannot do that with the technology that exists today. So it is inevitable that a technology change happens to get that data traffic to flow, and that will be through optical connections.
Yeah, absolutely. Which brings us on to our next point, which is the kind of the good work that you've both been doing in this area to help the data center networks. Chun, did you want to start by talking us through the micro optics that you guys have been developing?
Oh, okay. So we make a precision micro lenses and micro prisms, and everything can be. We use it's just called micro optics. It's very high next generation micro optics. We use a semiconductor wafer processing technology. So this thing is just like making semiconductor chips. We do all this lithography, etching, and developing and coding all these technologies. So we bring up a whole family of new generation of micro optics. And we think it is very helpful for us to increase the bandwidth and solve the problems like power consumption, space saving, and the lower loss, all these things. So
if you wanted to give the audience a little taster with your slides now, please do feel free. Okay. I'm going to mute while you do that, though.
Is this the full screen? It is, I guess, right?
Yeah.
Can you see the slides? So, the topics we call it in precision micro lens array unlocking high bandwidth data traffic. Okay. How this thing moves. All right. So this is the content I'm going to talk about, the solution to meet high band data traffic demand. And we believe the new avenue we want to explore called spatial division multiplexing, or SDM. And I will talk about the space advantage, power consumption advantage, cost advantage, manufacturing advantage. So they have a lot of advantages that really is needed. They are really needed by the data center. And this, so let's see this. The solution to meet the data, oh, okay. All right, it moves pretty fast. Okay. So we believe that to meet this demand is we need to make a read multiplexing in space. This means we use multiple fibers, they bundled together either like ribbons or ribbon stacks, or to carry a signal, or just to use like multi-core fibers. And not only we use this special fiber, we also make the component all processed together by integrated components. I mean, we have one optical device, it processes all these signals at the same time for all these multiple fibers, by multi-core fiber or fiber stacks. Let's the first one, I'll show an example of how we can do the space saving. This is a multi-core fibers, and it's being done by this, currently it's being done by this, let's increase the screen, it's done by the biconic fusion splicer. So they are have pretty high loss, like 2 to 3 dB loss, and the dimension is pretty big as well. So it is like, let's see, it's like 15 by 4 millimeters. It's very big. So we designed using micro optics. We designed this device. It's multi-core fibers and there's fiber lens arrays, and we make this micro prism etched by the same semiconductor process. And we expanded another lens array and coupled to these fiber bundles. Like this is several. So we make the space. The dimension is so tiny compared to the previous one. So it is like 1.5 millimeter by 3 millimeters. It's very, very small. So it's reduced the size of this whole thing size to is 1/50. So 1/50 of the original device. And if we have multi-core fibers, even 14 core, it become 1/100th of the size of the original device. Not only that, the insertion loss is only 0.3 dBs. It's like almost 10 times smaller than the previous one. So this one, if we use this newer generation devices, it's not only increase the traffic bandwidth by a factor of 7, it reduces the size to its 100th or 1/50th of the original size. And also the power consumption will be lower for the transmitter or silicon photonics, the front end, because the loss is reduced by a factor of 10. So this is a really, we got excited about this. With this new micro lens arrays, we can make these fancy devices that is much better than the previous one or the one has been used. And this is we have this is our technologies we used. Vapor processing. We use all this vapor processing to make these lens arrays. It has a power advantage. So let's move to the next one. See, we can make the prisms. You see the prism arrays, we also ask them. They are very tiny, and they can do a very high quality. We can do a very high quality prism, and they can integrate it with the lenses. So we integrate together, we can make the assembling of these new couplers very efficient and very fast. And previously you have to assemble 7 or 14 of them. Now is to assemble one of them. It has the same capacity as 14 fiber or 7 fibers. It depends on how many cores we have. in the fiber. So this is another device we made, integrated optical isolators, because when we have a transmission, we need to have an optical isolator to prevent the laser being damaged or the transmitter being damaged. And that has been done pretty in a smaller size. But with our new lens arrays, and we can make these things only 1/14 of the standard size. It's much, much smaller. And the performance is also excellent. So this, you can see this is the new isolator arrays. It's 12 of them optical isolators. And they function exactly as the original 12 isolators, but they are much smaller because they all integrate together. And these devices can be connected to the multi-core fibers or fiber bundles. They process all these signals at the same time. And this is done by using our micro lens array and other micro optics. We worked with our with one of our customers, and then we make this device. It works much smaller space and much efficient. So this device is our first time being exposed to our site. We just let people know we have done that with the advanced micro lenses we have. So this is the third example is the WDM devices. We have a 4-channel WDM devices, but now we integrated them together into 8 channels together. So the space is much smaller, and if we use some 750 micron cores, the device is much smaller, and also it's lower cost because a lot of the royalties in the optics can be used now. If you make individual ones, you have to cut the optics into very small pieces. When you cut the pieces, there's the edge effect. On the edges, you cannot use it, being damaged. Only the central part being used. A lot of royalty is being damaged, but these wafers were made in wafers in large quantities. We cut it. Previously, people cut it and used only central part. Wasted a lot of real estate space. Now we made them together, so we make the integrated device. So yeah, this is the one you can see compared to the previous one. This is the 4-channel. Now we have 32 channels. Use lens arrays. This is 32 channels. It has almost the same size as this one, the same size. Now we increase the capacity by a factor of 8. So that's 4 channels. Now it's 48 channels. So it's very tiny, but performance excellent. And there's a manufacturing advantage as well when we make the arrayed devices. So previously, when people, or until now, people making things, they use like the optics is not very precision. It's not precision. It's not accurate very much because it's not needed. We use the active alignment technologies. So whenever there are the errors in manufacturing, in the precision and accuracy, they're off. But you can always make adjustment to bring it back. But with arrayed optics, we don't have enough degree of freedom to do the alignment. In fact, the available freedom of alignment is only 12, and we need it in 78. There's a lot of freedom left. Not enough. Use the previous generation optics, but with our precision micro lens arrays, we can achieve basically passive alignment only with the assistance of active alignment. So we achieved a very high precision as well. So the performance is still very excellent compared to any individual ones. So this is a micro lens array. We use, you can see the precision is extremely high. And we use lithographic etching technologies to make these things. We can do a lot of things, micro lenses and arrayed and prisms. And this is any size we can make like very large range of sizes. The smallest size we can make is 50 microns. It's very small micro optics until millimeters, 100 millimeters. So we can make all kinds of micro lenses. This is another optical device. It's called optical circulator. It's very useful in bidirectional transformation of the data. You can see we make 8 of them together, so it's in an array, and this is the single one, and this is our one. So we have a lot of room saved. So this capacity is increased a lot, but the room is almost the same as before. You can see the performance, the test performance, they are excellent. There are any difference compared to the single ones you aligned, use active alignment method. But we use basically passive alignment method, we achieve the optimal performance for all these 8 channels. So when we make these arrayed devices and they combine with multi-core fibers or fiber bundles, this is a device is very scalable. I only demonstrated some of this, like 8 channels, 12 channels, but as long as we can scale it up to very high channels, there's no limit, and use the same technology. This is the technology is good is because it is scalable, and it can add another avenue to our data traffic issues we have now. Not only we can combine this technology, it's very compatible with WDM, we're very compatible with advanced modulation technologies. So they all work fine. They explore different directions. Combined together, we can. I feel very confident that we can solve these traffic issues. So this is a brief, very brief introduction of our macro lens arrays and our method for solving these traffic issues.
Thank you very much. Thanks, Chin. So I'm going to move on to Terry. Can you talk us through iLab's work to help support next generation data intensive workloads?
Yes, Keely, I think there's a couple things first, maybe just a baseline with what our labs is building and delivering. So I talked about scale-up networks earlier, and our labs really, the solution from our labs comes from two base components. And I'll try to show this and we'll see if it comes across on camera. One is a chiplet that's a little piece of silicon. It's about 9 millimeters square. That chiplet contains an EIC, a PIC, and logic to convert from electrical to optical. And then that's powered by a laser. And that laser is that size. That's a 16 wavelength laser that feeds the chiplet. And so what we do with those two components is those get, the chiplet gets multi-chip packaged with a compute chip, an SoC, a GPU, a CPU, or an FPGA, that sort of thing. And then the laser also goes in the server, and that powers the chiplet data path. And so where we're at now with the development of the technology is we're shipping those parts in engineering samples. They're being qualified, going through qualification processes for multi-chip packaging. And then you also go through a lot of new test procedures for instance, to set up the ecosystem to do not only electrical, but electrical and optical test of the solution. Because when you put the solution together, as opposed to traditional approach where you're only testing electrical integrity, you're testing electrical and optical integrity of the multi-chip package. So both the qualification of the test equipment, as well as how you build out the ecosystem for including, for instance, fibers inside of a server sled, and how that goes together. So the good thing about that from an our labs point of view, and we're going down the path of chiplets. Chiplets are used by the merchant silicon providers today. That's a standard approach to use chiplets for specialized workloads. And we're also using on the electrical side a UCIe standards standard package electrical interface, which is also being adopted by a large majority of the semiconductor producers. So it allows us to connect into their SoCs and do so with a chiplet, which is a known form factor.
Fantastic. And continuing with you, Terry, if that's okay, how do you kind of go about developing something like that, high capacity solutions for data centers? And are there challenges in doing so in terms of scalability and that kind of thing? Can you talk us through that, please?
Yeah, I think that is where, if you look at the history of our labs, we've spent a good amount of our history over the past many years taking technology from paper into actually making it and showing that it works. So we're producing silicon, we show it, we produce the lasers, we show those. The technology works to the specifications that we've laid out. The next step is, and this is where we're at in the journey of the company at the moment, is it's one thing to make, say, 10,000 of those parts, which we can do, and we've done. It's another thing to make 1 million a month, which is the process we're going into now. And so the work we're doing with the ecosystem, with the OSAT network around the world, is how do you bring in optical feature sets into both packaging, test, and high volume manufacturing at the level of millions of units a month. That's the challenge we're looking at now, and that's what we're working toward going forward.
Perfect. Thank you. Moving on to you, Chun, from your perspective, how have you advanced your photonic technology to help OEMs? And are there any kind of partnerships that you found particularly beneficial at all?
Yeah, as you can see from my presentation, we specialize in manufacturing high precision and high accuracy micro optics lenses and prisms. And we combine them, use the technology that is used to make semiconductors. So they are very precise. Furthermore, we believe that spatial division multiplexing is the way to add another bandwidth developed avenue to the current technologies we have, like advanced modulation and the WDM. Now we have spatial division multiplexing, and with these three things combined together, we can make a lot of new chips, new devices. These devices can help internet make traffic goes faster, storage bandwidth is even higher. So this is the things we are very excited, and we are already. I showed a few devices. We are making a whole family of devices that works together with this SWDM spatial division multiplexing, and with a lot of fibers and process them together, and they are being like WDM together, split, and also optical isolations and circulations, all these things all together. But because we have a very precise lens and can be made very tiny, very small, and so we can make the whole devices much smaller. So this is our goal. We can reduce the room or the space requirement for the data center. If we go to the data center, a lot of room being occupied by these instruments and components and cables. Now we can reduce them. I showed a few examples. The component can be reduced sometimes to 1/20, sometimes it reduced to 100th of their original size. This is much smaller. This will help equipment manufacturers like Ayer Lab to put these whole things into a very small package. And the cables, we don't need that many cables because each of the cables carries a lot of signals. So this is really, we think this help the data center can solve the issues. Also, the components I showed, they have a very good loss. I mean, the loss is very, very small. Even they use the passive alignment, but they are very precise. So they performed very well. The same as you made it use active alignment. So this is all the things that really helps the data center to reduce the problems you are facing, the power consumption, because we make the things lower loss. So you use like 1/3 or to half of the power you used to use to let the signal transfer from one end to the other end, because previously you lost a lot of power, so you need a higher power for the transmitter. Now you don't have that loss, so you can use the lower power, optical power from the transmitters, and then so you use less power for the less electrical power, and also you don't need that much cooling. The cooling requirement will be lowered. So all these things combined together make the data center operating much efficient. We can help equipment manufacturers, the data center operators, to help them to make these things faster. So this is we think we can do right now with our advanced technology.
Fantastic. And also, Chun, just to put the same question to you, you know, are there any challenges you've kind of found in terms of developing products such as that, you know, in terms of scalability and that kind of thing?
We have been developing components for years. I have been designing components for past 30 years. We do all kinds of micro optics components and lasers and also how to package them. So we don't have much challenge so far. We have been pretty smooth. When we made this component, because our technology has been developed for many years. We have this micro semiconductor process knowledge for 20 years. We have been working on this technology and working on these materials. We know what kind of material glasses we should use, what kind of silicon surfaces we should use, what kind of etching recipes. We have this whole set of skills in-house. So we make a very good quality product. And with the design, our experience, with our knowledge about the current component, we know how this thing is being made before. Now we know the newer generation is coming. Newer generation component, we are making it. So we don't have a lot of challenge so far.
So far. Excellent. Thank you. And the kind of the partnerships question to put to you, Terry. Are there any kind of important partnerships, relationships that IOLabs has found particularly helpful in product development?
Well, I think, you know, the way that the product that we have, the chiplet I mentioned, which we call Terrify, that is a pretty intensive design-in process with the designers of the SoC that we're pairing with, right? So it's not a matter of, you know, we don't necessarily make a chiplet and toss it over the wall to somebody and they take it and run with it. It's a very hands-on, deep co-design effort that the SoC provider, let's say someone making a GPU, we sit down architecturally and we work, you know, hand in hand over a long period of time to make sure that our silicon and their silicon integrates together and that the optics side of our silicon delivers the value promised to them from a data transfer standpoint. So our relationships with, you know, first with the SoC providers or the compute accelerator providers, starts there with designs, but it broadens out very quickly into the ecosystem of both fabricators and fab houses, as well as with OSATs who are assembling both the package, the multi-chip package, and doing tests, and then assembling that into, you know, subsystems that go into servers and racks of servers. So there's a huge ecosystem that we engage with our customers to deliver that solution. And that's not, I would say that's, especially in the way that we're using optics for scale-up fabric, which hasn't been done before. That is the pipeline to do that and the work it takes to do that over, as I said, 1 million units a month target. That's multiple years of work to get to that point. That's not something that's being done today. It's not, you know, it's not something that can be done necessarily tomorrow. But when we look at it, we think the 2026 to 2028 timeframe is when you will see those types of solutions come to the commercial marketplace. So we're working with a number of great partners to get us to that point in a few years.
Excellent. Thank you ever so much. So looking to the future a little bit, and I'm going to stay with you, Terry, for a minute, if that's okay. How do you see emerging technologies and applications such as AI and cloud impacting future development of the high-speed optical technologies in data centers, or are there any other factors you think may be kind of impacting the data center network?
Well, I think, you know, as a company, we've been around for a bit over 9 years, and I think early on our founders saw the need for high data transfer at low energy, at low latency. So they saw that a long time before we ever saw the first AI model come to market. But once AI models did come to market, when you look at, say, Q4 of 2022 or the first part of 2023, the explosion in usage model, and therefore the complexity of those AI models and the parameters it takes to deliver those AI models, that really put a lot of momentum behind the idea of how do you move data efficiently, enough data efficiently to keep those GPUs delivering the AI, the promise of AI. And so that really is driving a lot of the interest and momentum around implementation of optics inside the server environment. So I see that as kind of the beachhead. The AI side of things is the beachhead of what will drive this technology to marketplace. But beyond AI, there's a number of, both in cloud data centers as well as other subsystems that maybe are not a data center, that will be able to take advantage of optical interconnects for data transit.
Yeah, absolutely. And Chun, same question to you in terms of, you know, the kind of future of data center networks and optical technologies.
Yeah, I think there's a lot of exciting things happening in the data communication and data traffic arena. Number one would be, I would say, is optical interconnect at the chip level. Silicon photonics is a great opportunities for people who working in this field, and silicon photonics really integrate the optics together on the chip level. So it's very tiny, and the electrical, the current travels a very short distance. So the electric current travels very short distance, so they are very efficient. Optical signals are very close to each other, material is saved, and also the optical things can be processed in parallel. The parallel is very, very useful to us, because we are going to, next things I'm going to say is the scaling to the terabase network. When we have the network, we travel the data long distance. The spatial division multiplexing is matching perfectly with the silicon photonics, because they are parallel as well. The same data is being transferred in parallel. So now we can combine three tools we have. We have advanced modulation technologies, and then we have WDMs, either coarse WDM or CWDM or whatever other format of WDM, combined with the spatial division multiplexing. We have three tools. They are powerful tools, and one of them, the spatial division multiplexing, hasn't been fully explored yet. So we have all this. I'm confident we can really help the data center to solve the issues we are facing, and we are going to create a lot of opportunities. So I'm looking very bright in the future right now. It's better right now, and I think it's provide a lot of opportunities for many equipment and component manufacturers. For example, they are making the chips, silicon photonics companies. They are making these fibers, special multi-core fibers, and optical switching. This is a very important part as well. The large quantity of fibers, they're going to switch. We're going to make a dynamic work. So the switching companies will make good switches. They are very efficient and very fast, and a very high number of ports. Those are the opportunities for people to explore. And in addition, the power saving. We have to make a good components, good devices with very low loss. And silicon photonics already achieved that, because they use parallel processing. They use a very short electrical circuitry inside, and they even integrated the optics and the electrical together. We make a co-packaged component. All these things save electricity, and we make the lenses with lower loss for this passive components. That also requires a lower power from the transmitter side. So all this, we lower the power requirement down. So this is the part I think we provide opportunity for people to make this happen. And finally, I think there's an area we need to explore we can use AI to help us to make the networks more efficient. Because when people have been talking about the dynamic networks, how whenever with the existing infrastructures, whenever there's a need for higher data, we'll transfer the bandwidth to them. And this thing can be done with the AI help, with the large model calculations. They can give us a much faster, much efficient management of the network. But this is the software part. I think we have this present in front of us. Also, although we are now working on the software side.
Fantastic. Thank you ever so much. I'm going to touch on edge computing now. How do you think high-speed optics can facilitate a more seamless integration of edge data centers with the core data center network? Can I go with you, Terry, first for that one?
Sure, Keely. I think, for a long time, silicon photonics has been used inside data centers, and fiber optics have been used for long-haul datacom around the world. So I think that infrastructure exists and is getting better with every generation. I think what we are most focused on is how do we improve the efficiency and the effectiveness in the network inside of, primarily inside of a data center, but between, hundreds of racks. And we think about how do we connect those compute chips in those racks. And again, it goes back to the AI workloads that need to be running. The AI workloads need to be able to look at the GPUs and the memory associated with those GPUs across multiple racks as one kind of compute unit. So you can think about a rack, or actually multiple racks, as just one big compute node. And the only way you get there is through the implementation of optics in the connection of those compute nodes. So we do feel like both the edge data center as well as what people refer to as the core data center network gets massive improvement through the implementation of optics. And between data centers, let's say, that has been a place where optics and fiber optics and silicon photonics have been in play for a while. So I think that continues.
Excellent. And Chen, same question for you, please.
Yeah, well, with edge computing, it is very needed, because a lot of things like autonomous driving or some calculation, quantum calculation, they need a data center close to them. So the edge center is very useful, and it's making things more efficient. And because of this, we have different data centers located at different places. Obviously, the data fast transfer from center to another place, from one center to another center, it has become critical. This is a very long distance, and we need a lot of data to be transferred very fast without latency. And optical network is really fit into this. And with the three things I mentioned before, the spatial division multiplexing, WDM, and advanced modulation technologies, we can really have the capabilities to transfer data from one place to other places very fast and without errors. And this is not possible with the old network. With the old network, with the wires, we have latency, we have limited bandwidth, and that's impossible. That's why the data center had to be just centralized. Now we can decentralize it and make it distributed in all the places. So the fast data transfer is a must. We must have that. And the current technology we have made is possible, the fiber optics technology, with the new lens, with the new method for making these things, make them low loss, is really helpful, to make this happen.
Excellent. And looking ahead again, and we've kind of touched on this a little bit, particularly Yusheng, but in terms of the other exciting opportunities that you see in the future for high-speed optics in the context of data centers, Terry, what's your views on that?
We get real excited when we look at the simulations we have done and continue to kind of refine around what optics can do inside of a data center, and the new ways of thinking and working with the data center. For instance, AI workloads, they generate tokens. That's a figure of merit of data that they generate. And token generation over time is one way to measure the effectiveness, productivity of your AI workload, your AI agent. So humans, we can absorb a certain amount of tokens per second. And maybe that's up to the 40, 50 tokens per second range, but that's about the extent of how much you or I can read and absorb if you're dealing with, let's say, an AI agent. But with optical interconnects, you can go much faster generation of tokens and transfer that allows machine-to-machine agentic workloads to happen, which don't happen today. So that's something that the integration of optics into AI models enables new ways of thinking around how AI is put to use, and really starts to allow an AI agent from multiple AI agents to work together on a problem that then results in something that, that we see, that we benefit from. But that level of data transfer and work only happens with optical interconnects in those AI models. So that's a new area of thought going forward that we're really excited about.
Excellent. Wow, exciting. Thank you. And Chen, did you have anything you wanted to add to that in terms of the exciting opportunities ahead for high-speed optics in terms of data centers? I know you did touch on it a little bit already, but if there's anything else you see as exciting coming up?
Yeah, I think I see we can make the data center even because when we make the data center, it's more efficient, use less power and a smaller space, and we can build more of these centers. We can distribute it even further away because with the speed of optical fiber optics transfer speed, we can transfer these things very fast, very close to people, very close to the user. So for quantum computing, for some like AI models, calculations, and for some autonomous driving, all these things, they need data really fast, and they need to be transferred very fast as well. And optical technologies really fit into this very well. So I think there's a lot of opportunities being created around this optical technology. They can help many industries to develop. For example, for the instrument, for these fiber cables, for these connectors. So there's a lot of industry being benefited from the advanced technology in fiber optics data communications and data transfer. This is I see is a very bright future. And the thing is, we have a readily available technology to tackle this. It's not something we are going to, we being stuck. We have technologies ready for this that can be deployed right away.
Yeah, excellent. So that was kind of the questions that we discussed. Is there anything else that either of you think would be important to mention to our audience with regards to high capacity optics within data centers? I can see you nodding, Terry. What?
Well, I think.
Would you like to go first here?
Yeah, I think first of all, thanks for having us here on the webinar. I think there's a lot of great technology being discussed today, but exciting on multiple fronts. Let me step back a little bit and just give a quick summary of what our labs is doing. First of all, the growing complexity and size of AI models that I've talked about is creating unprecedented demands for today's AI architecture. And that's really breaking the back of the existing infrastructure using copper and electrical interconnects. So there needs to be a new solution there, and interconnects that are through optics, that helps to break down those bottlenecks and helps move the data to move AI forward. So, our labs is really created the first standards-based optical I/O that's commercially viable to fit in the scale-up networks of those AI machines, which enables that future of AI. And the market opportunity for us is substantial in the way that it's going to, in the way that we balance high bandwidth, energy efficiency, and low latency required for that AI infrastructure. So I would just say that, as a close from our lab side, we're very excited about the opportunity and where the company's positioned and the partners we're getting to work with. We've talked about our work with NVIDIA and Intel and the hyperscalers and others. It's just a very exciting industry to be a part of. And it's very exciting to be in the space we're in, because we feel like we are going to unleash the future of AI.
Yeah, It's exciting times. Amazing. And Chun, same to you. Anything else you'd like to mention before we close that we perhaps haven't touched on yet?
Yeah, the Focuslight is a company we started with making lasers, but a lot of high power lasers. Then we expanded our product portfolio to many different areas, to medical and to high power solid state lasers, and to autonomous driving, to LiDARs. And now we see the opportunity. We want to move into the telecom business. We used to make fiber optics, micro lenses, micro prisms, all these micro optics things. Now we think we're going to move into the component division, and we use our existing technologies to demonstrate this. We haven't really fully decided to go to the component division or not, or the arena or not, but we want to make components to demonstrate the capabilities of our micro optics. Because with the model, with the components I showed here, it proves the precision and the accuracy of our micro prisms and micro lenses. So this is the part we got excited, because we think this is a way to show our capabilities in micro optics, because we use the micro optics to make the combined components, and they are very efficient, much better than the current ones. It's a new generation component. We want people to work with us, to collaborate with us, use our micro lenses and micro optics to make these components. So this is the things we think will benefit everyone in the industry. If you come over with us, work with us, and we demonstrate this thing works, it will work for you as well.
Excellent. Thank you very much. I'm conscious we're getting short on time now. We've had a couple of questions, but rest assured we can forward the questions on to the chaps to answer afterwards. Just thank you so much for joining me again today. I've really appreciated your time. That brings us to the end of today's webcast. To our audience, it will remain live on the Electro Optics website for the next 12 months. So if you know anyone who's missed it and would like to catch up, then they'll be able to view it for the next 12 months. And that's www.electrooptics.com. Obviously, there won't be a live Q&A on catch up, so obviously to bear that in mind. So all that remains is for me to say thank you so much to our expert panelists, to Chun and to Terry, to our sponsor Focuslight, to David and the Europa Science production team working in the background. And last but not least, thank you so much to everyone who's taken the time to tune in today. We really appreciate it. Thank you very much. Goodbye.
Thank you, Kitty. Thank you, Terry. It's a pleasure talking and discussing with you.
Yep, you too. Have a great day.